Good afternoon everyone, this is Mr. Ish. Thank you for joining me in this video. I am going to be presenting a topic here on verification of trigonometric identities. I understand this is a step or two back in terms of the calculus because we are delving here back into the topic of pre-calculus, and I've been eagerly putting out videos in calculus. We are stepping backwards only momentarily because before we get into integral calculus, it is important to revise these trigonometric identities because they play very much a role in those questions that you will see. Without further ado, look over here. In the verification of trigonometric identities, these are kind of like proving questions. You have to prove a certain statement is what it is. Let's start with a very easy one. If someone says sine x cosecant x is equal to 1 and you have to prove it, you prove these types of questions using trigonometric identities or the fundamental definitions that you know. You know you're multiplying a function with its reciprocal, you'll always get a 1 because cosecant x is the same as 1 or sine x, and because these cancel out you end up getting 1 and you prove it. So just starting here with a very easy one, you know, anytime you're multiplying a trigonometric function with its reciprocal, not inverse but reciprocal, you'll always get a 1. Likewise, if you have something which looks like this, tan x times cotan x, you know you have to prove 1. Well, the proof here involves nothing more than you rewriting the cotangent in terms of the reciprocal of the tangent, and you have this and you say 1 is equal to 1, so this is done as well. So this is pretty much the gist of what we're looking at today, but slightly harder than this because the verification of trigonometric identities involves proving that the left side is equal to the right side. If you look at this one, cosine square alpha minus sine square alpha is equal to 1 minus 2 sine square alpha, you basically have to prove that the left side is equal to or similar to the right side. You can do this in one of two ways. If you think these alphas are just x's, it doesn't matter, these are just variables, it could be any letters here. You can think about the Pythagorean identity, sine square x plus cosine square x is equal to 1. You can solve one in terms of the other. Let's solve for cosine square x. Cosine square x is equal to 1 minus sine square x, and here the x is synonymous with the alpha variable you're seeing. If you were to substitute this in terms of this right over here, you can do 1 minus sine square alpha, which is substitution right over here, minus sine square alpha, and you solve this out, you get 1 minus 2 sine square alpha, and you would be proving that the left and the right side were indeed equal, and you'd be done. The other way you could have done this is by understanding this other identity, the cosine 2x y whatever, let's just stick with the alpha variable over here, is equal to one of three things. It can be equal to cosine square alpha minus sine square alpha. It can also be equal to, remember this identity over here, think back to the trigonometric videos I presented. It could be 2 cosine square alpha minus 1, or it can be 1 minus 2 sine square alpha. Look over here, cosine 2 alpha is equal to any of these three things, and you're seeing both of those right here. One is right over here on the top, which mirrors this, and the other one is right over here, which mirrors this. So essentially this entire equation over here is basically saying cosine 2 alpha is equal to cosine 2 alpha, and this was another way you could have proved the same thing. You could have used the Pythagorean identity, which is perhaps the easiest way, or you could have done this way right over here. Both are legitimate techniques. These ones here before us are not difficult by any means. Looking at the top one, we are automatically thinking about a Pythagorean identity. If you know tan square identity, which you know was tan square x plus 1 is equal to secant square x. If you manipulate just this in terms of tan square x, you get secant square x minus 1. This right here becomes secant square theta minus 1. All I've done here is solve for tan square x and take 1 on the other side. Plus 4 is equal to secant square theta plus 3. When you open this over here, you get exactly what you're looking for. Secant square theta minus 1 plus 4 is plus 3 is equal to secant square theta plus 3. So the top one is done. Now for the bottom one, it's not hard. You just have to condense this part right here. Cosine x plus sine x, and you condense it by opening up the tangent into this function right over here is equal to secant x. Multiply this over here, you get cosine x plus sine square x over cosine x, we'll do over 1 is equal to secant x. We have to still prove that all of this is equal to that. We'll do a common denominator here, cosine x, you get cosine square x plus sine square x is equal to secant x, and we know we're actually right there because this Pythagorean identity, cosine square x plus sine square x is equal to 1. You essentially get 1 over cosine x, which is equal to secant x, and it's done. So this one is done as well. It required just doing algebra over here and recognizing this Pythagorean identity, cosine square x plus sine square x is always equal to 1. Now for this one over here, it's not hard. You have to somehow show that this block here on the left is equal to that. And I think a good way to proceed would be just looking at the left side only and working with the left side and somehow making it convert into secant x. And we can do that over here by using a conjugate. Look, conjugate of the denominator, you'll do 1 minus cosine x and you multiply with the conjugate of the denominator. You know the conjugate, the opposite sign, 1 plus cosine x. Multiply the top with the top and bottom with the bottom. You get secant x times cosine x. A function multiplied by its reciprocal is always 1, so plus 1, right? Secant x times cosine x will be 1. Minus 1 times 1 will be a minus 1. Minus 1 times cosine x will be minus cosine x. That's just opening the top. And you know you're basically looking at something like this, FOIL method, first out, inner last. That's all I'm doing over here. Now we'll do the same thing in the lower. 1 times 1 is a 1. 1 times cosine x minus cosine x. Remember, when you're doing true conjugates, you don't get intermediate terms. You can go directly to the end terms. 1 times 1 and minus cosine x times cosine x. The intermediate terms would have cancelled out. Now look here on the top, we basically get secant x minus cosine x, and here on the bottom we get 1 minus cosine square x. Now the item over here to focus on is the numerator, because we have two different functions here in the numerator. And how do you know you should focus on one side versus the other? Because everything should ideally be presented in only one function. And you look at that area where there are more than one function presented, and that's right here in the numerator. Let's do that. 1 over cosine x, which is secant x, minus cosine x over 1 minus cosine square x. I haven't done anything with the denominator. We'll work here in the top. You do a common denominator here, you have a cosine x. 1 goes in cosine x, cosine times, you get minus cosine square x right here on the top. Because here you're going at 1, here you're going at cosine x. And that's how you get this. And then here you get 1 minus cosine square x. Now what do you do over here? Well, it's not hard. This right here is basically something over 1. You flip everything around the denominator. You get 1 minus cosine square x over cosine x times this denominator rational aspect will be flipped around. You get 1 over 1 minus cosine square x. These things will cancel out. You essentially come up here with a 1 over cosine x, 1 over cosine x, right? And then this right here is equivalent to exactly what you see over here. But it wasn't hard. It was basically more algebra than anything. So basically these verifying trigonometric identities by convention are the type of questions where you prove the left side can be manipulated to become identical to the right side. And you know we have to somehow show this is equal to that. And you know this might be one of those conjugate multiplying questions where you're doing rationalizing of the denominator. And I'm going to do that. I'll do secant x plus tan x, nothing on the top, but I'll rationalize it with the denominator, which will affect the top by multiplying everything with the conjugate. See, the conjugate of this denominator is exactly what you're seeing with an opposite sign. And that exact item has to be multiplied with the numerator. Let's do the denominator, because when you're doing conjugates, you eliminate the intermediate terms, you only look at the end terms. You have secant x times secant x, you'll have secant square x. You'll have minus tan x times tan x will be minus tan square x. You don't have to do the intermediate multiplying at all, because true conjugates lose the intermediate terms. But you won't lose the intermediate terms on the top. You get secant square x. You know you're doing the FOIL method here, which you should be able to do in your head. You'll have plus 2 secant x tan x plus tan square x. This is what we have so far, and this is what we have to work with. Let's put a important trigonometric identity over here, which we know tan square x plus 1 is equal to secant square x. Is one of the three Pythagorean trigonometric identities. Let's manipulate it such that if we solve for 1, we have secant square x minus tan square x. You see, I take the tan square x on the other side. 1 is equal to secant square x minus tan square x, which is what I'm seeing right over here. This right here, all of this right here is potentially equal to 1. So what else can we do over here? We basically have just the numerator now to deal with. Secant square x plus 2 secant x tan x plus tan square x over 1. There's no need to write over 1. Now we have to just deal with this in a good manner and somehow solve it out. It is nothing more than you looking at it as something like this. A square plus 2ab plus b square, a square plus 2ab plus b square should be nothing more than, in terms of factoring, basic factoring, a plus b whole square, a plus b whole square. So when you rewrite this in terms of the factor, because you have basically something which is presented to you in this form, you have to convert it into this form, which mirrors exactly what you see here. You're rewriting as this secant x plus tan x, right? And then you're doing this whole square and you're done basically. This question here where you have to prove this is equal to that is seemingly tricky, but it is actually visually very easy if you can remember basics over here. The only reason why I say this can be done in the unsophisticated manner or the sophisticated manner. The sophisticated manner is this, where you understand what a reciprocal is, just the basic concept of a reciprocal. If you know tangent has a reciprocal of a cotangent, you're looking at it in terms of this. 1 over tan x is basically equal to cotan x. And you know this right here, the reciprocal of cotangent x is basically tan x, and you are literally done just by doing that recognition of what a reciprocal is, just by doing that, because you're looking at it already. Here you're looking at the reciprocal of tan x. What does reciprocal mean? It means 1 over something. And here you have 1 over something. So this right here translates to this right here translates to this, and you're pretty much done. That's a sophisticated way of doing it. The less sophisticated way of doing it is when you're doing more effort than that's needed. And you would do it this way. You would do 1 over sine x over cosine x, right? Plus 1 over cosine x over sine x. And I'm not going to rewrite this here. I'm going to solve this out. You'll flip everything around. You get cosine x over sine x, but sine x plus sine x, you're just doing fractional flips over here, is equal to cotan x plus tan x. But in terms of order and adding, order does not matter, right? In terms when you're adding or multiplying and there's no minuses involved, order does not matter. This is the same thing as saying tan x plus cotan x, right? Because order does not matter. But this right here is a better way of doing it, just by purely understanding what a reciprocal is. You're looking at the reciprocal of it and the reciprocal of this, and it's a one-step question. So when you're looking at a question which looks like this, sometimes seemingly we find ourselves at a loss over here, like how do we proceed about it? But there's a giveaway in this question. The giveaway is this -1. Why is it a giveaway? Because if you just do 1 over 1 over here, right, now you know you're forced to do fraction algebra. Common denominator between this and this is going to be 1 minus sine x, and that is exactly what you need to do. 1 minus sine x goes in this one time, so the items on the top stay the same here, cotan x. But look over here, 1 goes in this, how many times? 1 minus sine x times, right? Is equal to cosecant x. We don't really need to do anything with that over there. Now what do we do over here? We can open this stuff in the numerator. We'll have cosine x cotangent x minus 1 plus sine x, or 1 minus sine x. Now we can open up this cosine and cotangent. What will we get over there? We'll get cos square x over sine x minus 1 plus sine x. We can do over 1, and we have 1 minus sine x over here. All of this has to somehow equal to cosecant x. Let's find the common denominators over here between this, and this, and it'll be just sine x. Sine x. Sine x goes in sine x one time, so you get a cosine square x over there. 1 goes in that sine x times, you get a minus sine x. 1 goes in this sine x times, multiplies with that, you get a plus sine square x, right? All over 1 minus sine x, which is over its 1. Now look, cosine square x plus sine square x is really a 1 using the Pythagorean identity. So what you really end up getting here on the top is a 1 minus sine x over a sine x, right? Which is this right here, sine x. This stuff on the numerator, cosine square x, sine square x, Pythagorean identity, brought in this 1. And you are still left with that minus sine x. Now flip this around. You get 1 over 1 minus sine x. We're flipping this lower denominator around. This right here will cancel out with this right here. You get 1 over sine x, right? Which will give you exactly over this, what you're seeing over there. 1 over sine x is cosecant x. These questions are easier than they appear. They're basically dealing with the cofunction identities. The cosine of an angle is equal to sine of its complement. If you do cosine 90 minus x, that's the same thing as saying sine of x. Think about it. Cosine, if this x was a 40, you're saying cosine 90 minus 40 of 50 is equal to sine of 40. The cosine of an angle is equal to sine of its complement, and the sine of an angle is equal to cosine of its complement. So exactly works both ways. So this cosine pi over 2 minus x translates into sine x. When you multiply sine x with its reciprocal, you will of course get a 1. So that top one is done. And the same thing falls over here. The cosine of an angle is equal to sine of its complement, the cofunction identity. The sine of angle is equal to cosine of its complement, and you know you're going to get a tan x, and you're done over here as well. Here, this question, verifying that this is equal to this is nothing hard here. The book is hoping that the student here has probably forgotten the concept of even functions and odd functions. If you remember that cosine is an even function, which it is, you know cosine of minus x is the same thing as saying cosine of x. Because for an even function which have a symmetry about the y-axis, the negative x doesn't matter. Because for even functions, you know f of minus x is equal to f of x. Same thing. That's for an even function. And sine is an odd function. For an odd function, f of minus x is equal to minus f of x. So the question writer here is hoping you've forgotten that, but you haven't. And you proceed with this. You convert cosine minus x into cosine x because it's an even function. In the denominator, sine minus x becomes a minus sine x because it's an odd function because of this property, 1 minus sine x. What are you going to do here? You're going to multiply everything by the conjugate. 1 plus sine x. Look over here. We will do cosine x with this and cosine x with that. You'll get cosine x plus sine x cosine x. Here in the denominator you'll get only the end terms, 1 minus sine square x. 1 minus sine square x can be simplified using the Pythagorean identity, where you have sine square x plus cosine square x is equal to 1. If you solve for cosine square x, you'll get 1 minus sine square x. So here in the denominator, you're getting cosine square x. Remember, cosine square x is equal to 1 minus sine square x, which is exactly what you're seeing here. 1 minus sine square x substitutes for that. In the numerator, you isolate cosine x. You get 1 plus sine x. In the denominator, you got cosine square x by means of this. This cancels out with this exponent right here. You get 1 plus sine x over cosine x. Now all you have to do is separate everything around the positive sign. You're getting 1 over cosine x plus sine x over cosine x, which you now know will be secant x and tan x. Secant x and tan x, and you'll be done. We could officially write over here, we'll get secant x plus tan x, and your question will be done. We basically separate everything around this denominator and then around this denominator across the plus sign to yield this part right here. Let's look at this one. This here is a cofunction identity. For cotangent, you have a tangent coming together. The tan of a angle is equal to the cotangent of its complement. Likewise, the cotangent of a certain angle will be the tangent of its complement. The same function, same identity holds true, but for secant, it'll be with involvement with the cosecant. And likewise, the reverse of that. The sine and the cosine are together. The tangent and the cotangent are together in these cofunction identities, and secant and cosecant are together in these cofunction identities. And that's what we're looking at over here. You'll have secant square y, nothing we can do with that, but cotangent of this angle, resulting angle, will be equal to the tangent of the complement, which will be y is equal to 1. Now we are looking at the Pythagorean identity, where tan square x or y, whatever letter, is equal to secant square x. All you have to do is manipulate this somehow to get rid of a function. Everything should be here in one term, and this tan square y is the same thing as tan square y without the parentheses. what do you want to eliminate over here? I would eliminate the tan square x. Tan square y or x is equal to secant square x minus 1. You see, when you're solving for this, you take the 1 on the other side. Here we rewrite everything, but we'll bring the y in it. Tan square y is equal to secant square y minus 1 minus secant square y minus 1 is equal to 1. This minus will affect everything here by means of the parentheses. Secant square y minus secant square y plus 1 is equal to 1. These cancel out and 1 is equal to 1. So let me say over here again, if it was not clear for any of you, for these cofunction identities, when you're doing sine of an angle, complement is equal to cosine of that. The sine of an angle is equal to cosine of the complement, and these work backwards in flip-flop. For tangent, it's also the tangent of an angle is equal to cotangent of its complement. It'll also work backwards. For the same type of identity, it'll be here secant of an angle will be equal to cosecant of its complement, and it'll work backward. That means here you could have put cosine, here would be sine, here you could put cotangent, here would be tangent, here you could have been cosecant, here would be secant. So you can flip-flop all of these. But this right here are the cofunction identities you should be aware of. So what looks here as seemingly complex question is not that hard, because we're looking at sum and difference formulas over here. The first thing you want to recognize is tan x plus tan y divided by 1 minus tan x tan y. Look something which is eerily familiar to tan x plus y, because that's the formula for tan x plus y. Here look on the top, sine x cosine y plus sine y cosine x. You're looking at sine x plus y formula, aren't you? Sum and difference formula, the sum sine x plus y will give you that. When you're looking at the cosine aspect over here, you're looking here, because of this minus sign, it clues you into exactly this. It's x plus y, not x minus y, but it's x plus y. So sine x plus y divided by cosine x plus y should be equal to tan x plus y, and your question is done. Just, it was that easy. But let's quickly review these sum and difference formulas, because there's 6 of them that you need to know of, and I'll write them out here in a very expedited manner. When you're looking at sine x and a y, and you can have a plus or a minus here, in terms of how we would review it, it would be the sine x cosine y plus and a minus sine y cosine x. If you're looking at the top sign, you hold the top sign. Sine x plus y is equal to sine x cosine y plus sine y cosine x. When you're looking at sine x minus y, you have the same thing here but with the minus sign, but it flips around for the cosine formula. Cosine x plus minus y would be cosine x cosine y. You see these subtle differences here. Here you'll have a minus on the top and a plus here on the bottom. With the plus, you'll bring a minus here in the open expanded formula. With a minus, you'll have a positive in the expanded formula. Here you'll have a sine x sine y. What about for the tangent formula? It's exactly mirroring the sine x plus y in terms of the signs. Tan x plus minus y would be this. You would have tan x and then you'd have a tan y. I'm putting the signs momentarily. You'd have 1 tan x tan y. So here are the differences with the tangent formula. When you're doing the tan x plus y, you're going to put a plus over here and you'll put a minus here. When you're doing the tan x minus y, you put a minus with the minus formula, but you'll put a plus with the minus aspect. And you can see the signs are right here. You would read them out exactly as you see in it. See it, tan x plus y is equal to tan x plus tan y divided by 1 minus tan x tan y. And tan x minus y is equal to tan x minus tan y divided by 1 plus tan x tan y. So these are the 3 formulas right here, sum and difference formulas that you should be aware of, because they can pop up in these identity questions. So let's keep this fun going. Here's another question. It basically is relying on this property over here, that the sine function is an odd function, therefore a negative angle affects it in such a way that the sine over here becomes minus, just like an odd function would. You'll convert everything over here by means of that odd function property. The plus will become a minus and the angle will just become a plain y, because this minus will transfer right over here. If you just do the multiplication over here, these are basically conjugate. You'll end up with 1 minus sine square y based on the specific trigonometric identity where sine square x plus cosine square x is equal to 1. If you solve for cosine square x, you get 1 minus sine square x. So this right here is equal to cosine square y. all of this is equal to this, and that's exactly what you have to show. Right and left sides are now equal. This question over here is kind of slightly difficult because you have y's and x's and y's. It would be difficult to convert everything into one variable, and you don't have to. All you have to do is show that this side is equal to this side. The best way to proceed with this type of question is to break everything into its sub definitions. You know, tan is sine or cosine, cotan is cosine or sine, so that's what I mean by sub function. Like you're breaking it up into its basic definition by making sure the variables do not get commingled. Where you have a cotan and a y, you'll put a sine y in the denominator, cosine y in the numerator. And you're doing the same thing here with the denominator. Also, you have sine x over cosine x, and here you'll have cosine y over sine y. We're not going to do anything over here. We'll just continue from right over here. You have to do the common denominator here in the numerator aspect right here. The common denominator between cosine x sine y is cosine x sine y. Cosine x goes in this, sine y times, so here in the top you get sine x sine y. This is just fraction adding, that's all. Sine y goes in this, cosine x times it multiplies with this. You get cosine x cosine y, but this right here is all over this right here on the bottom. You can bring everything here together into one clump. Sine x cosine y over cosine x sine y. If you were to flip this entire denominator out, it would flip over and you'd multiply. It'd be like a fraction dividing. You could cancel these out literally, such that you only have this part on the top and this right here. You would have this eventually. Sine x sine y plus cosine x cosine y over sine x cosine y. Now the easy part. You have to split everything here across this positive sign, and this is how you would do it by means of what I'm showing you right over here. This and right over here that. When you look at this first shape over here, you have sine x sine y divided by sine x cosine y. The two sine x's will cancel out. You'll see these two sine x's will cancel out. You'll just get sine y over cosine y. Here's your plus sign. When you're looking at the items and then the second shape, cosine x cosine y divided by sine x cosine y, the cosine y and the cosine y's will cancel out. You'll get cosine x divided by sine x. Now just look over here. Sine y or cosine y is equal to tan y. Cosine x divided by sine x is equal to cotan x, so we're done. What you end up getting over here is what you actually wanted. Tan y plus cotangent x. And you are done. Slightly difficult question, but not too hard. Maybe more confusing and as to how you proceed over here. You have to proceed with this type of question in the correct manner, otherwise you'll get lost somewhere along the way if you proceeded with an incorrect route. This right here is by no means a difficult question because sine is an odd function, its reciprocal must be odd. And if you remember that cosine is an even function, its reciprocal must be even. That's all what you're looking at over here. In the numerator, you're basically looking at 1 over sine minus x in terms of its definition, reciprocal definition. In the denominator, you're looking at 1 over cosine of minus x. When you remember that this is odd and this is even, you're looking at 1 over minus sine x, and this here becomes 1 over cosine x. When you flip everything around, you get cosine x divided by minus sine x, and that eventually leads you right over here. And this question is completed. Here before us is an interesting one. You have the square root of this 1 minus cosine x divided by 1 plus cosine x, which when simplified using whatever procedures should equal to this 1 minus cosine x divided by absolute value of sine x. And this 1 minus cosine x would be in a circular parentheses. The sine x is in an absolute value. How you go about proceeding with this type of question is to rationalize what you see here in the denominator. 1 minus cosine x is in the numerator, but you must rationalize everything with the denominator with 1 minus cosine x. And then 1 minus cosine x, what you rationalize in the denominator stays in the numerator in terms of the same expression. You're multiplying conjugates over here. And another technique over here is not to split everything in the numerator and the denominator into its own denominator. Separate radicals. Remember, this property root a over b is the same thing as root a divided by root b. Law of radical. It's a very important property. When you're multiplying in the denominator, you have conjugates. You get 1 minus cosine square x. The intermediate terms will cancel out. You can see that for yourself. In the numerator you get 1 minus 2 cosine x plus cosine square x. That's what you'll get. A square minus 2ab plus b square is what you're really getting here. When you refactor this into its more condensed format, you will get, actually you didn't even have to multiply this. I was kind of naive when I opened this up. You were basically looking at what you saw at the very beginning, 1 minus cosine x multiplying by itself twice. You could have written this numerator part right over here. Here you're just taking it back to this form right here. And here you have to use the Pythagorean identity where sine square x plus cosine square x is equal to 1. Sine square x is equal to 1 minus cosine square x. So this right here is the sine square x right over here, sine square x. When you do the square root of a power, you end up with just the original function because you get 2 over 2. Remember the radical in exponential form, this is right here, this is what I'm talking about. If you're doing a square root of an a square, you're looking at a square over 2, which is really equal to a to the 1. Here in the numerator you're getting 1 minus cosine x. You can keep that in this parentheses. Here in the denominator you're getting a square root of a power square, so you're going to get sine x. The only reason why sine x here will end up in the absolute value and this can stay here in the non-absolute value is because of the properties of sine x being an odd function and cosine x being an even function. Remember, sine of a minus angle will remain a minus sine, whereas the cosine of a minus will become positive, right? Cosine of a minus will become positive cosine. So why does that have to do anything with the absolute value? Because you cannot take a negative sign and take a square root of it, because you end up having an imaginary solution. You only can get away with a proper real solution with the positive values. Hence, because of the properties of odd and even functions, you have an absolute value around here, the sine x. But this question has been completed. We have this right here, expression mimicking exactly what you see here. In these type of identity questions, anytime you're seeing powers of 4s and 3s, possibly 2s, you always have to be thinking that now you're having a question which is just basically going to involve factoring. That's it. It's just disguised in the form of trigonometric functions, but it is just basic factoring. And you know, within the normal course of algebra and precalculus, you'll always learn factoring techniques first, then you'll get into trigonometry. So you should be able to factor something like this. When you're looking at this, you're looking at cosecant square x minus 1 times cosecant square x minus 1. Right? That's, if you were to open this up, you would get right exactly here. But this can be all rewritten as cosecant square x minus 1 because it's the same thing multiplying by itself twice. You can write it as this. And now you have to think back at this Pythagorean identity where cotangent square x plus 1 is equal to cosecant square x. You have to think about one of these identities. And if you were to solve for cotangent square x is equal to cosecant square x minus 1, this right here can substitute for right over here. You get cotangent square x square, and when you open it you get cotangent 4x, which is exactly what we were looking for from the very beginning. So the question is done. This one right here is not hard. If you look at it, you have a square minus b square, except you're involving to the powers of 4s. You can do secant square x minus tan square x, because we have to show that this equals that, multiplied by secant square x plus tan square x. If you were to multiply all of this, you'd end up back exactly here. Now we have to think back to this identity, tan square x plus 1 is equal to secant square x. If you were to manipulate the tan square x and take it on the other side, you get secant square x minus tan square x, right? If you take tan square x, it's equal to 1. Secant square x minus tan square x equals 1, which is what I'm seeing over here. This all equals 1, and then you just have secant square x plus tan square x. Now what do? You substitute for secant square x in terms of this original one. Secant square x is also equal to tan square x plus 1, and in this area right here, you substitute what you see over here. Tan square x plus 1 plus this other tan square x. When you simplify all this, you get 2 tan square x plus 1, which is what you're looking for right over here. In different order. 2 tan square x plus 1, 2 tan square x plus 1 when we're done. This one over here, proving this side is equal to that side, is very familiar to the previous question, except here we're dealing with these two functions. a square minus b square treated as such, cosecant square x minus cotangent square x multiplied by the exact same thing, cosecant square x plus cotangent square x. And we're looking at this identity, Pythagorean identity, cotangent square x plus 1 is always equal to cosecant square x. And remember, these x's can be replaced by thetas, alphas, betas, any kind of variable. But that right there is our hinting identity that we're looking at. If you solve over here for 1 is equal to cosecant square x minus cotangent square x. Exact same premise as the previous question here. Mimicking what you see over here, this becomes a 1. But then going back to this original function, is there anything we can do over here? We can. If you solve for the cotangent square x is equal to cosecant square x minus 1. You take 1 on the other side, and that's exactly what we'll do. Cosecant square x plus cosecant square x minus 1. See, you took the 1 on the other side and you solved only for cotangent square x. And you end up with getting the final answer, 2 cosecant square x minus 1. And that's exactly what you had to show was right over here. And we're done. Not a hard question by any means. Anytime you see questions like this, where you have some sort of an expression but it's not associated with any exponent, you know you might be thinking about rationalizing, because here everything is to the degree, variable degree or order of 1. You want to rationalize. You have to convert this side right here into this side over here. You'll rationalize the denominator almost always. Not exclusively, but almost always. You'll rationalize here by using the conjugate. And you do the exact same thing on the numerator side. This with this, this with this. These are conjugates over here. You'll only get end terms. You won't get the intermediate terms. In the top, you'll get cotangent x times cosecant x plus 1 over. Here you get cosecant square x minus 1. You multiply this, you'll get cosecant square x minus 1. Come back to this identity, and I'm going to show you this one right here. The one right here from the very previous question, cotangent square x plus 1 is equal to cosecant square x. Somehow we got to look at this in this form. If you take the 1 on the other side, the cotangent square x is equal to cosecant square x minus 1. So this substitutes for this, and that's exactly what we have here in the denominator. Cotangent x times cosecant x plus 1. Here you're not of any benefit opening the numerator because it'll just add more work. Here you get cotangent square x. You can cancel this out for this exponent, and you end up getting cosecant x plus 1 divided by cotangent x, which is exactly what you have to show right over here, and your question is done. This question here plays very well into what I was saying earlier, that anytime you're seeing these exponents of 3s and 4s and sometimes 2s, we have a factoring question in our grasp over here, except it's camouflaged in the form of a trigonometric function, but the basic premise of factoring is still the same. You have a cubed minus b cubed, and that's exactly what you have to do, is view it in factoring. A cubed minus b cubed will formulate into this expression, a minus b times a squared plus ab plus b squared. You'll have a tan square x plus tan x plus 1. A minus b times a squared plus ab plus b squared, using that numerator item. Here you'll still have tan x minus 1. When you cancel out this and this, your remaining expression is exactly what you see over here. And this seemingly difficult question is very easy and quick to be done. This question likewise is similar to the previous one, except you might have a little extra step at the end. You have a cubed plus b cubed, and you have to use that as your guide as to how you proceed. A cubed plus b cubed has to be factored or opened up, or expanded is what I mean, expanded. You're basically expanding this, and you'll get a plus b times a squared minus, remember a cubed plus b cubed is a plus b times a squared minus ab plus b squared. You'll have a sine beta, cosine beta, and then plus cosine square beta. Over here in the bottom you have exactly what you see. You're never going to do anything with that until it comes time to cancel things out. If you're not able to cancel this out, it means your original factoring template is wrong, that you used the wrong template. You cancel it out. Now somehow this has to look into that, and the only way it can is if you look at the original trigonometric Pythagorean identity, you know, where sine square x plus cosine square x is equal to 1, because you have a sine square x and a cosine square x these two together come into a 1. You get 1 minus and what's left over, sine beta, cosine beta, and that right here completes your question. This question here was rather tricky one because I have to admit to you all, I tried once initially by whatever technique I was picking initially, and it came out wrong, that I was doing it in the wrong way, until I came up with the second way, which should have been what I had picked the first time. But sometimes you have to pick and choose or use trial and error to come up at the right technique. So I'll admit to you all, my first method of trying this question out, like the most obvious one, came out wrong. The most obvious way would have been for you to start going into the basic functions like cosine x minus, and then you start looking at these in this form, 1 over sine x because that's cosecant x, and then cosine x over sine x because that's a function of this, and then you start doing cosine x minus cosine x over sine square x. If you open up all of this, this is what you end up with, and you end up automatically putting a over 1 here, and then you go to the procedure of fraction algebra, and that came out not the very best way of doing this. The best way of doing this, so I'm going to put like a little x over here, and we're going to come right over here. The best way of doing this question was to see a cosine x here and a cosine x here and isolate it. If you look at the cosine x and you isolate it from this expression, you can. It goes into the first expression 1 times, but there is a cosine x over here. It's just camouflage in the cotangent x. Remember, cotangent x is cosine over sine. Well, and that's exactly what you do. You isolate the cosine from here, and what do you end up getting? You get here a cosecant x. When you isolate a cosine x from right over here, from this function here, or which looks just like what you're seeing right over here, the cosine from here, you end up with 1 over sine x. That's what you end up with, and you can re-multiply everything over here and you'll end up with that. Cosine x times 1 is a cosine x. Cosine x times cosecant x times 1 over sine x will give you cotangent x. Now, look over here, you can rewrite this. 1 over sine x is the same thing as saying cosecant x, but cosecant x will multiply by itself and you get cosecant square x. And now you have to think back at this trigonometric identity, the Pythagorean identity. Cotangent square x plus 1 is equal to cosecant square x. Cotangent square x is equal to cosecant square x minus 1. And that's what we see over here. Cosecant square x minus 1, right? But we see here with a minus sign. If you multiply everything here by a minus 1, multiply by minus 1, you can flip this around and you get minus cosecant square x is equal to minus cotangent square x. So this will come right over here, a minus cotangent square x. You'll get cosine x times a minus cotangent square x, and that, when you open this up, will give you your final answer. You'll get a minus cosine x and a cotangent square x, and you'll be done. So you can see how this question played out in a slightly convoluted manner. The most obvious way was not the right way. You have to somehow pick a cosine from right here and proceed with that. Use this trigonometric identity, hit it with the minus ones, you can flip it around and bring it down over here in terms of your substitution. And that leads you to your final answer, and then you're done. We won't look at an alarmingly more questions. We'll just look at some more and that'll be it. And there are many identities I've never even presented with regards to my video, this one or the previous videos, like the sum to product and product to sum, because as I realized, the focus of this set of videos are towards the calculus, and some of those identities, trigonometric identities, you just do not see very often in calculus. I'm trying to keep these videos practical from a calculus point of view. Were this just a series of trigonometric videos, and we would be looking at all of those other trigonometric identities. For this question over here, again, verify that this is equal to that. It's a no-brainer if you think about it in this sense. Sine square x plus cosine square x is equal to 1. When you're solving for cosine square x, you're taking sine square x on the other side, and then you will be substituting that for right over here. You end up getting tan x times cosine square x, because cosine square x represents part of this Pythagorean identity when you solve for cosine square x. And then you have to open this up. You get tan x times cosine x, and I could have probably done that better because I have to open up the tan x as well, right? You would have sine x over here over cosine x. When you would multiply this across, you would get a sine x and a cosine x. But if you think about this specific trigonometric identity where sine 2x is equal to 2 sine x cosine x, you basically just are seeing this less the 2 aspect in it. So you're basically looking at just half of sine 2x, because you would have this thing, everything over here divided by 2 if you had an imaginary 2 over here. So you basically end up having this phenomenon or this identity but in a half version, and you are done with this question. This here is not difficult to prove at all. If you're looking at sine cube x and sine x, you can just start with isolating sine x. When you isolate sine x, you get a sine square x in the first part and you get a cosine square x in the second part. And I'm just carrying that down. You know the Pythagorean identity, anytime you see this, it's equal to 1, and you're multiplying by sine x and you're getting a sine x. So this part right here is done. It was not difficult and it was very quick. Let's do another quick one over here. How about this? This was one question right here. Here's another one. We have cosine x, and these are all from a trigonometry book. You have a tan square x plus 1, and you have to show that this right here is equal to secant x. You know exactly where this is coming from. You have another Pythagorean identity here. Tan square x plus 1 is always equal to secant square x. So you rewrite everything as cosine x times secant square x, because this entire expression solves into this or simplifies into that, and then you have equal to secant x. You have cosine x times 1 over cosine square x. This 1 cosine x will multiply, will cancel out. In a reciprocal manner with this power, you get 1 over cosine x, which is synonymous with secant x. So this question is done as well too. When we're looking at this question over here, it is rather tricky of a question, because you would normally be working from this side or this expression towards the left, but here we have to work from the left towards the right, which is normally it's customary when you're doing very fine trigonometric identities, you work from the left side to the right side, except here our left side expression is unorthodox by nature. How you know the manner by which you'll proceed is this right here. This radical 1 plus cosine x, the fact that it's in the denominator, somehow you got a radical in the denominator means we rationalized something, and the only thing we could have rationalized was a numerator over here. View it in this way. You're basically looking at 1 minus cosine x square root multiplying by the rationalizing conjugate, you can call it that, 1 plus cosine x or 1. Bring this all based on this radical property, root AB is equal to everything separated, or everything separated multiplying is equal to everything under a unifying radical. So bring everything under a unifying radical. You'll have a 1 minus cosine x, and you'll have a 1 plus cosine x. Here on the bottom, you'll just get 1 plus cosine x, so that's not hard by any means. The bottom part is done. We just have to deal with the top numerator item. You have this big radical. You're going to be multiplying two conjugates. You're not going to get any intermediate terms. Just do the extreme items. 1 times 1 and minus cosine x times positive cosine x. You'll get a 1 minus cosine square x, and you already have the denominator done, 1 plus cosine x. Think back to the very basic Pythagorean identity. Sine square x plus cosine square x is equal to 1. If you solve for sine square x, you take cosine square x on the other side, right? And that's exactly what you have over here. It substitutes for sine square x over, and you have 1 plus cosine x. When you're doing the radical or the root, square root of sine square x, you're going to basically just get this absolute value sine x over, you'll have 1 plus cosine x, and your question will be done. You have to think back and understand why the sine x comes here in these absolute value brackets. It has to do very much with the odd function nature of the sine x, because as you know, sine of a minus angle becomes a minus sine value, whereas cosine of a minus angle, because cosine is an even function, it retains the positivity in terms of the value. So you do not end up with a minus radical or minus within a radical. You use the absolute value over here. That is such that your value within the radical sign must always be a positive. Hence it's playing out in that way. But our question here is done. You can see it's done. At a very quick glance, you would look at this quickly and say, hey, this is a cofunction identity where the cosine of an angle is equal to sine of the complement. But that's not the case because of two reasons. One, you're getting a minus value here, and secondly, you have a positive over there. The cofunction identity would have looked something like this. Cosine of 90 minus x would equal to sine x, and then vice versa. You can flip the functions around. But this is not a cofunction identity. This is one of those sum and difference type of identities where cosine x plus y is what you're looking at is equal to cosine x cosine y minus sine x sine y. That's all you're doing over here, and you're using this format right over here. You'll do cosine x cosine of 90, which you know will be a 0, minus sine x and then sine of 90. I was going to put literally the number 90, but that's fine. Pi over 2 is equal to 90. Cosine of 90 is basically a 0. You get cosine x times 0 minus sine x. Sine of 90 is just a 1. This zeroes out. You essentially just get minus sine x and you're done. So this question here is done. So it was not hard. It required you to know this sum and difference identity for cosine, which is similar to this type you have for sine and tangent, but this was that type of a question, not hard. This trigonometric verification is similar to the previous type of question, except here you're using the difference identity for sine. You know the difference identity for sine would be sine x minus y would equal sine x cosine y. It would not be a plus, I was going to say a plus. The signs remain true to the function of sine. It would be minus sine y cosine x. So all you have to do is follow the scheme, x's and y's, x's and y's. You'll have a sine pi cosine x minus sine x cosine pi. Sine of pi is 0 basically. All of this will 0 out. You'll get basically minus sine x, and cosine pi is a 1. Actually cosine pi is a minus 1 because cosine of 0 is a 1, but cosine of minus 180 or cosine of positive 180 is a minus 1. So here you get a positive answer sine x and you're done. Right, so again I'll say sine of 0 and 2 pi will be equal to 0, but cosine of 0 is equal to 1 and cosine of pi or minus pi is equal to minus 1. Why am I saying minus pi over here? Because if you're looking from 0 and you're going pi in this direction, it's the same thing as you're going minus pi but in a clockwise direction. Remember, positive angles are counterclockwise, negative angles are clockwise, but positive pi and minus pi put you right here at the 180 degrees anyway, so the value for both of these will be a minus 1. For this trigonometric identity verification from left to right, 2 sine y cosine y times secant 2y is equal to tan 2y is a very easy question disguised as something very difficult, because you're looking at one aspect right here which is an identity on its own, and here's another one on its own. Look at this, 2 sine y cosine y is basically equal to sine 2y, and these could have very well been x's because you know sine 2x is equal to 2 sine x cosine x. The other identity over here, secant 2y, is the same thing as looking at 1 over cosine 2y. You're just doing the reciprocal. Now you're basically looking at sine 2y over cosine 2y, which naturally by the basic definition of tangent should be tan of 2y, and that's all you have to do and you were done. This here is a rather tricky one which has kind of crept up into our questions over here. This has to do with this type of a function, trigonometric identity we're talking about, where you do cosine x plus y is equal to cosine x cosine y minus sine x sine y. This is where we're heading here with this, except here the x plus y will be numerical variables, cosine x plus 2x, because x plus 2x will give you that. You just have to plug this into this form right over here. You'd get cosine x cosine 2x. Then here with a positive you always end up getting a minus. You'd get a sine x and then a sine 2x. But now you're seeing cosine 2x and sine 2x, which can generate something. You know, sine 2x generates 2 sine x cosine x, and cosine 2x can generate, and I've shown you this at perhaps the very beginning of this video, it generated 3 different items. One was cosine square x minus sine square x, the other was 2 cosine square x minus 1, which might be the most applicable one here, and the other one would be 1 minus 2 sine square x. This one is what I would go with, because everything here must be in cosines. I won't bring a sine square into here at all, because you know this thing generates 3 different items. Think back to the identities videos I presented before. You have to do substitutions over here. Cosine x is this cosine x. Cosine 2x, this right here. 2 cosine square x minus 1 minus sine x, which is this right here, and then sine 2x, which you substitute for this. 2 sine x cosine x. This will be a little bit of work, but it won't be hard. You have to open this up. You'll get 2 cosine cube x minus cosine x minus 2 times the coefficient here is a 1. You get a 2 sine x. You get a sine square x cosine x. All I've done is just open this entire thing into this. But I know I still have to do something with this sine square x because I need everything in cosine. And you have to use this trigonometric identity, the Pythagorean identity is equal to 1, where you solve for sine square x, you get 1 minus cosine square x. That 1 minus cosine square x will shuffle and find its way right over here. You'll get 2 cosine cube x minus cosine x minus 2 times 1 minus cosine square x times cosine x. I would have been better off had I brought the cosine here with the 2. But I still have to open this up. I get here 2 cosine cube x minus cosine x. This is why I was saying it's going to be work. This 2 cosine x will multiply with these items. I'll get a minus 2 cosine x and I'll get a plus. See, minus times this minus will give you a plus. 2 cosine square x times cosine x will be 2 cosine cube x. Bring all the like terms together in this final hurrah and we're done. 2 cosine cube will give you 4 cosine cube x. Minus cosine x minus 2 cosine x is a minus 3 cosine x, and we are done. Just because we've seen the previous question with the cosine, I want to do another one here with the sine and see how this would open out. We don't want to bring a cosine in here unless we have to, but if we do, we have to convert it back somehow using identities back into a sine. With regards to the previous question, we would use this in the same manner. We'd view it like this. 3x would be x plus 2x, and we'd go from there. You know the sine formula over here with regards to the identity, we're using the sum and the difference identity. We'll do sine x cosine 2x plus sine 2x cosine x. Let's make this neat. Cosine x. These cosines have to be eliminated and these sine 2x's have to be dealt with. Cosine 2x. Cosine 2x can be one of 3 things, you know. It can be cosine square x minus sine square x. It can be 2 cosine square x minus 1. It can be 1 minus 2 sine square x. Sine 2x, you know, I've shown you is, I'll write it out here again. Sine 2x is basically 2 sine x cosine x. From these 3 here for cosine 2x, I would pick this one right here, because it doesn't bring the cosine in it at all. And let's start plugging away. You have sine x, which is this, multiplied by cosine 2x. I'm going to use this 1 minus 2 sine square x. 1 minus 2 sine square x. Then I have this positive sign. I have sine 2x. I have to bring this 2 sine x cosine x. 2 sine x cosine x. This cosine x will multiply with the second cosine x. You'll get cosine square x. The only way we can best eliminate this using the Pythagorean identity, sine square x plus cosine square x is equal to 1, where we solve for cosine square x, which is equal to 1 minus sine square x. And we'll plug that right over here. So let's open this up. We get sine x minus 2 sine cube x plus, we'll have 2 sine x, and in place of cosine square x, using this identity, we'll substitute 1 minus sine square x. When we open all of this, we will get a number of items. We'll get this part here has been opened up, but we have to open up this part right here. We'll get 2 sine x minus 2 sine cube x. Here, last step is just bringing in the common terms. Minus 2 sine cube x minus 2 sine cube x, you'll get minus 4 sine cube x. Sine x plus 2 sine x will get plus 3 sine x, and you will be done. This right here will be a good final answer. In a matter of sophistication, you could write the positive one first. 3 sine x minus 4 sine cube x. Either way, they're both good answers. For this question over here, you have to verify that this left side is equal to the right side by the fact that you're seeing the numerator here, sine x plus y. You know you're dealing with a sum and difference type of identity. You have to open the stuff here in the numerator. You'll get sine x cosine y plus sine y cosine x over cosine x cosine y. Now when you see something like this, there are two ways you can proceed with this question. The hard unsophisticated way or the easy sophisticated way. The hard way would be you look everything here in the numerator and you start multiplying again with the conjugate here in the numerator and denominator and see how that deals and plays out. The other way you can do this is by splitting everything over here across the positive sign into two different items, and you can deal with them separately and things will cancel out. When you deal with this first side, you get sine x cosine y over cosine x cosine y. This is the sophisticated but the less work. The sophisticated way of doing question is called sophisticated because you're doing less effort and getting the same result. Here you're getting a sine y cosine x over cosine x cosine y. Cancel things out. Cosine y cosine x cosine x. Here you get sine x divided by cosine x, which is tan x. Positive sign. Here you get cosine y divided by cosine y, tan y, and you're done. It mirrors that and you're done. I want to end the video with a formal discussion of the double angle and the power reducing trigonometric formulae. I have probably talked about this in detail prior in a previous video, but I don't think I've really gone into that. The double angle formulas are these ones right over here. The ones which look something like this: sine 2x, cosine 2x, and then you have tan 2x. And they equal something, and you know what these equal. The power reducing formulas are the ones which look like this. Sine square x can be reduced into something, cosine square x can be reduced into something, and tan square x can be reduced into something such that the power is reduced. You see these exponential powers of 2, the degree of 2 is reduced by the power formula into the degree of 1. And this is what I'm talking about. Sine square x becomes 1 minus cosine 2x over 2. You see how the square has been replaced by a power of 1. Cosine square x becomes 1 plus cosine 2x over 2, and the tan square x becomes the sine square x divided by cosine square x. You'll get 1 minus cosine 2x divided by 1 plus cosine 2x. But I want to show you the derivation of all of these formulas, and that's what I mean with the formal discussion of these two. You know these ones over here, and what I'm going to do is going to go over these ones first. Then we'll come back to these and we'll show how each of these are proven. And then that'll be the end of it for this video of mine. So let's look at these double angle ones. We'll do step by step. The first one you want to look at is sine 2x. You know is equal to 2 sine x cosine x. And the only reason why I'm doing a formal review or introduction, however you want to call it, of these two, because these will show up in calculus. And how do you actually show that this shows up? Because of the very nature of the double angle. The double angle comes basically from this term right here. You're doubling the x. X plus x is 2x, so you're doubling it. So if you think back to the sum formula for the sine, you'll have sine x cosine x plus sine x cosine x. And when you combine it all together, you get 2 sine x cosine x, and that's how you derive this one over here. For the cosine 2x is exactly the same. You're looking at it in terms of this, the doubling of the angles. You know the formula for the sum for cosine is going to be cosine x minus sine x sine x. And this is how, when you do cosine 2x, you combine all of these terms. You get cosine square x minus sine square x. But you know this thing right here generates 3 different items. And I'm going to show you how, and I've shown you this before in another video. If you take a look at the Pythagorean identity, sine square x plus cosine square x is equal to 1, and you manipulate this, you can get the other 2 ways. If you solve for sine square x, you get 1 minus cosine square x, right? And then you plug that right over here in this form right here. You get cosine square x minus, and you're solving for sine square x, which is 1 minus cosine square x. When you open up all of this parenthesized items, you get 2 cosine square x minus 1. So that's how you get another of the items. Now here in this original identity here, the Pythagorean identity, if you solve for cosine square x, you get 1 minus sine square x, and you plug that right over here in place of cosine square x. You'll get 1 minus sine square x, then you have this original sine square x, and when you combine all of these, you get 1 minus 2 sine square x. So the other ones, these other ones are shown to you right away. Here's one right over here, and I've shown you this before in this video and in another video, but these are the double angle formula for cosine 2x. All of these three, and they're derived using this and from an extension of this one right over here. Let's look at the tan 2x next. The tan 2x one is by no means hard. It's double angle over here because here again you're doubling the angle. See, x plus x is a doubling of an angle, right? X plus x is 2x, that's doubling. You have to use the formula you know for this, the sum formula for tan, and you know that'll be tan x plus tan x divided by 1 minus tan square x, which would have been tan x times tan x. The original formula would be tan x plus y is equal to tan x plus tan y divided by 1 minus tan x times tan y. But here tan x gives you tan square x. When you simplify all of this, which is not much at all, you'll double the items here in the numerator and you'll get 1 minus tan square x here in the denominator, and this right over here is a double angle formula for tan 2x, which is equal to this. Let me show you something over here. If you look at this 2 tan x divided by 1 minus tan square x, you can look at it in terms of its basic functions. 2 tan x is 2 sine x divided by cosine x. 1 minus tan square x is 1 minus sine square x divided by cosine square x. If you do this 1 over 1 and you solve for everything in terms of simplifying it, then nothing will happen with the numerator, it will stay as is. Here in the denominator you get cosine square x minus sine square x divided by cosine square x. If you do this fraction algebra and you flip everything around, what you'll end up getting is cosine square x divided by, here you will have cosine square x minus sine square x. And remember, you can always do this on your own on a separate sheet. When you simplify all of this cosine x simplifies with this. What you end up getting over here is 2 sine x cosine x, right? 2 sine x cosine x divided by cosine square x minus sine square x. But what are we doing over here? We're showing that this right here is equal to the double angle formula for sine divided by cosine, right? It's sine 2x divided by cosine 2x, because one of the cosine 2x out of those three was this, and sine 2x is always equal to this. So we are showing here that tan 2x is the same thing as saying sine 2x divided by cosine 2x, which is the same thing as showing that. So here's another way of looking at the double angle formula for tan. Tan 2x is equal to sine 2x divided by cosine 2x. But the main item you want to know is this item right over here. We'll look at the power reducing formulas next. The power reducing formulas will show up quite a bit in integral calculus, so it makes sense to know them. We'll start with this one right over here. Sine square x is equal to 1 minus cosine 2x over 2, but we'll show how we actually come up with this. How do you actually derive this? It comes from this one right here, the double angle formula for cosine. If cosine 2x is equal to one of those three things, is this one right over here. This one right here, 1 minus 2 sine square x, and you actually solve for sine square x. What do you get? Minus 2 sine square x is equal to, you take this 1 on the other side, you get a minus 1. Then you take the minus on the other side. Minus goes on the other side, 2 sine square x is equal to, it flips this around, 1 minus cosine 2x. And now you solve for sine square x. Because it's power reducing, you're reducing the power to an expression which has no exponent. And that's helpful in integral calculus, because you're trying to simplify it by getting rid of the order, the exponent order. You take the 2 on the other side, you get this. So you've shown how you can derive the double angle formula for sine, because the power reducing formula for sine has been derived here. It comes from the double angle formula for cosine. That one over there. I'll show you next for the cosine square x and the tan square x, and we'll be done with this video. The power reducing formula for cosine square x is this one, 1 plus cosine 2x divided by 2. And how does it derive? It derives from the double angle formula for cosine again. Cosine 2x is equal to one of those three things, three separate things, but one of those is this one, 2 cosine square x minus 1. And I've shown you how you derive that. If you solve for cosine square x, you'll end up right over here. 2 cosine square x is equal to cosine 2x plus 1. Cosine square x is equal to cosine 2x plus 1 divided by 2, and it has been shown. Again, this one right here, power reducing formula, very important in integral calculus, especially trigonometric substitution techniques, is derived from this one over here, the double angle formula for cosine. The power reducing formula for tan square x is not hard, because you can imagine tan square x would be equal to sine square x divided by cosine square x. But what were the power reducing formulas for sine square and cosine square is exactly what you put over here. For sine square x, if I remember correctly, it was 1 minus cosine 2x over 2, and for cosine square x it was 1 plus cosine 2x divided by 2. When you flip this denominator around, these 2's will cancel out. They'll flip. Your final answer will be 1 minus cosine 2x divided by 1 plus cosine 2x, and this right here is your power reducing formula for tan square x. So it's not hard by any means. It is dependent on you knowing the sine square x divided by cosine square x power reducing formulas. You bring them together and you come up right over here with the eventual formula. So the 3 double angle formulas I've shown you and the 3 power reducing formulas, very important for calculus, as we will get into those integral calculus questions. So keep all of this in mind, and everything I've shown you with trigonometric verification in the previous parts of this video. And that'll be it for this video. I hope you enjoyed this video. I certainly did. Stay tuned, many other videos coming on the way. Feel free to leave any comment or any questions you have or any concerns, and I'll address them real quickly. Thank you for watching. Have a nice day. Bye.